Aloha, Richard Halverson here, and this is ITS148. And today I'm gonna do some programming projects out of Chapter 19. So let me share my screen. And today I'm gonna start with 19.2. Binary search trees. Okay, let's go look at see what that is. First of all, let me just quickly take about a minute and review what a binary search tree is. And it is a structure that looks like this, where we have data, and each of these pieces of data is stored in a data structure or an object, and in that object it also has the address, so to speak, or the index, or however this happens to be implemented underneath, the memory address presumably, of a left child. It's got, from there you can get to the left child, or you can get to the right child. And so a binary search tree is where the elements are stored such that when you do what's called an in-order traversal, they are all in order, in alphabetical order or in numerical order. And this makes it very easy for you to search. So like if you're looking for 57, you start out at 60, and 57 is less than 60, and so you go down here, and it's 55. 57 is greater than 55, so you go down in this direction, and lo and behold, there it is. So you end up you're able to search data, search for things in the tree much faster. To create a binary tree, of course, here's a nice animation, and if let's say we're going to insert 22, then that's going to go. We start at 50, and 22 is going to go on. We find a leaf node position. We find an empty spot where the one we're entering will fit to keep the tree in order. So it's going to be less than 50, so we go to the left. It's less than 25. Well, there's no node down there, so that's the place for it. So when we insert this, we see that it goes down here. If we're going to insert, let's say we're going to insert 24 now. So if we change this to 24, and that's going to go, it's less than 50, less, it's less than 25, less, it's greater than 22, so it's going to go down in this direction. So when we insert it, we see that it goes over there. Okay, so that's a binary search tree. Let's go to the problem that we're working on. We're going to do 19.2 today. I think I'm going to use the drawing board here. So in this problem, we define a perfect binary tree. And a perfect binary tree is one where all the levels are filled. So you know, if we're looking at a tree like this, let's say that something with a 5 in it, that's a perfect binary tree because all the levels are filled. Let's say we do 3. Is that a perfect binary tree? No, because there's a level here that's not filled. But if we were to make it full, then it would be a perfect binary tree. So for one level, it's just how many nodes are there for one level. See, this is a level. takes 1. This is actually a 0 level binary tree. And for 1, it takes its number of nodes. Let's look at number of nodes for perfect P. So for 0 level, it is 1. Hold on a second. All right, and for level, this is level 1, level 2. If the number of nodes is going to be 3, and for a 1, 2, 3 level, let's say it's 2, 4. This isn't perfect yet. This can be 6, and this can be 12. Now it's perfect. The number of nodes here is going to be 1, 2, 3, 4, 5, 6, 7. Okay. Now, so we need to be able to know if a tree is filled. And so the way that we can figure it out is if we have the level, we should be able to figure out how many nodes there are in a full tree. So let me just, yes. Okay, so in our binary search tree class, there is a method called size, or not a method, a property called size. And so if we have a binary search tree, we can know its size, which is the number of nodes it has. So so this would be size. Think of this as size. And so for a perfect binary search tree that has only one level, the size is going to be 1. For a perfect binary tree that's got 2 levels, the size is going to be 3. For a perfect binary tree with 3 levels, the size is going to be 7. Well, these numbers, this one is 2 to the 1 minus 1. Okay. This is 2 to the 2 minus 1. This is 2 to the 3 minus 1. 2 to the 3 is 8. 8 minus 1 is 7. 2 to the 2 is 4. 4 minus 1 is 3. 2 to the 1 is 2. 2 minus 1 is 1. So if we know the size, no, if we know the level, the level, okay, level equals height minus 1, right? No, plus 1. Plus 1. Yeah, okay. Because the height of this height, the height of a single node tree is 0. The height, if the tree only went down to here, the height would be 1. If the tree goes down to here, the height is 2. So you take the level, or you take the height, you add 1 to it, then you get the level. This is level 1, level 2, level 3. So this is height minus 1. That's a property. Height is a property. So so you can plug height plus 1 in for that exponent. Okay? Okay? You with me still? All right. So with that in mind, we just need to add a method into called isPerfectBST, which looks at the BST, which looks at the tree and sees if the it takes the height and it does this formula here. It does this formula, and it sees if the height, using the height with this formula, gives you the size. Okay, it gives you the size of the tree. So let's go on further here. This thing tells you everything you need to know. So let's look at this exercise. Use this thing. So let's take a look at that. I'm going to copy that, and I'm going to go up here and I'm going to go to it. And this here is what they ask us to use to debug our code. And really, it gives us the BST class. And so okay, so first of all, I'm going to copy all this, copy it all. First I'm going to do Control A and then Control C, and then I'm going to go over to my notepad and I'm going to do paste. And so here we have it here. So let's work with it over here. And so they give us the whole BST class, and with the BST class we get of course we get insert, but we get gets. Okay, so let's look at the properties. The properties are where it starts, the root node, and the size of the tree. So as you add or delete nodes, it's going to update this size property. So you always have the size property. Now you also have a delete is empty, clear, get root. Oh, we have to write the height to get the height. And in fact, back in exercise 19.1, we actually write that. Okay, so I'm assuming that you've done exercise 19.1 already and are going on to this exercise, because this exercise gives you the answer to 19.1. But so here we are, down here in this is what you submit, or this is what you would submit. You finish this, you finish up this. In other words, you just write your code for is perfect BST. You put that there, and then this is what you submit to this. Okay, that's what you paste in. You only submit your MyBST class. All right, let's go back to our code here. And so we're starting here, and we've got MyBST class already, or no, we've got BST class up here already. This is the class we have to include in there so we can create a basic binary search tree, and we have all these methods already to be able to create them, create a node, to insert in the node, to search. There's a search function, and getting the size and so on. And then of course we have to have a tree is made up of tree nodes, and a tree node it's an object. It's something we have to define, because we not only have to have a storage place for the data, but we also have to have a storage place for how to get to the next node on the left and how to get to the next node on the right. See, so there's two more places that it has to store stuff. And so this is what the tree node class looks like. So this is where it stores stuff, and then this is how you get to the next node, and this is how you get to the left node. This is how you get to the right node. This is how in other words, this is how you get to the left subtree, and this is how you get to the right subtree. So here's my BST class, and look, lo and behold, it already has the height method right there for us. And so we just have to write this method, and we get the code here all set up already for debugging, so we can actually just run it. When we run it, it'll first check to see what an empty perfect tree, if an empty tree is a perfect tree, and yes it is, and then you enter in a bunch of numbers, and it's going to create the binary search tree, and then it's going to tell you whether or not it's a perfect tree or not. So let's to know if it's a binary search tree, we just have to write first. So let's see, it's either going to be, okay, if the size, let's see, it's called self. If self size, so I'm just looking at how many nodes it has in it. If it's equal to 0, then we know that in other words, it's empty. Then it's a perfect tree, so we can return true. Capital true. Okay. Now if it goes down this path, it's just going to return. So we don't actually have to put an else if, because if it gets to this point, then it's still false, or then it's not true, or it's not returning. It hasn't returned yet. So you can say if, and now we have to figure out. So I'm not going to put an if yet. Now we have to figure out what the so we have to do this formula here. 2 to the height minus height plus 1. That's going to be the that is the test. We have to calculate this value, and that's what size should equal. So we have size. So that value is, so I'm going to have a variable called num nodes. Okay, so first of all, I need to know the height of the tree. So height equals, that's what we have here. That's this one. So we're going to use that, obviously, so that's going to equal to self dot height. So that's the height. And then we want to go exponent. The exponent is equal to height plus 1, right? That's what this is. Height plus 1. Oh, that's the level. I'm going to call it level. And then we're going to do level 2 to the level. Okay, so then I'm going to say num nodes equals num nodes for perfection equals 2 to the level minus 1. Now, because of operator precedence, it's surely going to do this first. So if the level is 3, it's going to compute 2 to the 3 powers 8, and then you're going to subtract 1 from it, and you get 7. So if the height is 3, then and the number of nodes in the tree is equal to 7, then we know that we have a perfect tree. So because so let's test that. If self.size is equal to num nodes for perfection, then return true. Okay. And then if we get all the way down to here and we still haven't returned, then we can just return false. Okay, so I say that this is my method to test if the binary search tree is perfect. Okay, so I tell you what, let's test this out. So let's first of all, let's go to here, and let's test it out with the. I'm gonna clear this, and let's test it out with the data that that it gives us to try. It is this tree here. So that's going to look like this. It's going to be, we're going to start it with 9. And then we're going to add an 8, and 8 is going to go, 8 is less than, so that's going to go down here. And then it's going to go to 7, so 7 is less than, so 7 is going to go down here. And then it's 87, 87 is over here, so. And then it's 78, that's less than 80, it's going to go down over here, and then it's less than that, so 78 is here. And then 98 is going to go 9, 87 is bigger than 87, so 98 is going to go here. Okay, here's the binary search tree. Now, is that perfect? No, it's not. It's not full. There's actually a space here that's empty, and then there's actually, so then, okay, yes. So if that were there, if there was something there, then it would be perfect because wait a minute. Yeah, that's right. Because the height would be 1, 2. The level will be 3, and at the third level, it's all full, and so that means at the second level it's all full, and so on. So yeah, okay. So so let's run this program. Let's go to my desktop, and this is this program here is test.py on my desktop. Save that, and I can run it by going py test.py. Oh, okay, no errors in my thing. Okay, so I'm gonna just copy this. No, copy this. Paste. Oh, there it is. And it says false. It's not a perfect binary tree. Now let's actually insert in see, I'm going to put something in right here. So I'll tell you what I'm doing. I'm going to make this 19. So that'll work. Make this 19, and this can be 10. Okay, so that's a binary tree, 19. Okay, so that's a binary search tree. A binary search tree is the node on the left is less than the node, and the node on the right is bigger than the node. And that's a recursive definition. So as you go down, as long as a binary search tree is the node on the left is less than the node, and the node on the left is a binary search tree, and the node on the right is greater than the node, and the node on the right is a binary search tree. Okay, so that's a definition of a binary search tree. So let's type this binary search tree, and I'm just going to start from the top. So let me run this again, and I'm going to type in 19 space 8 space 87 space 7 space 10 space 78 space 98. Okay, so that's all of the nodes, and it does, and I don't know how it's going to turn out, but it'll be full. And we say, is it a perfect tree? Yes, it is. It's true. So so you can see how it was built by the order in which I typed them in, and that is this was first, then the 8 went in, and then the 87 went in over here, and then the 78 went 19, no, the 10, 19, no, wait a minute, the 7 is 19, 8, and then 7 is here, so this is the fourth one, and 10 was 19, 8, and then it's greater than 8, so it goes here, that's an empty, so that was 5, and this was 6, and this was 7. So anyway, Now, now that we're convinced that our code is correct, you just need to copy this into this, and click submit. And that should work. All right. I hope that helped. Thanks for watching.